Okay, so let's pick up there. Now, we are going to talk a little bit about this psi and the relationship to the orbitals. And so how to get from psi, the wave function, to orbitals. So psi is a function that is a solution to the Schrodinger equation. It is called a wave function. And so it has the general form of a wave with an exponential decay away from the nucleus. And so if I were to draw some waves here, and I were to do it in red for psi for 1s, it basically looks like this. Oop, and it does an exponential decay, and so that's going to be psi for the 1s. And then in green, if I do psi for 2s, it's going to start at the same place, although let's just start it at the same place. We're close to it. It's then going to come down and approach 0 from the negative portion. And so a psi 2s has a positive and a negative portion. We're starting to see what looks like a wave here. And then for psi for 3s, we would actually start up here. We would actually go down, come back up, and then approach from the other side. And those are just one attempt to show you that these are wave functions. They are waves. The electron is always closest to the nucleus, going to have the highest value for psi, and that's because it is attracted to the nucleus. And then it is going to do some sort of waving as it goes away from the nucleus, meaning some sort of sine wave with an exponential decay. All right, so psi squared is the probability density. The probability density, and again, we're not going to talk about why this is, but let's assume that it's true. Probability density is just going to square psi. So that's going to just basically make it squared of the function before. So the red one, which was always positive, is still always positive. And that means that the probability density, that's going to be the probability per volume of finding the electron. And the probability is at a max closest to the nucleus, so that is the place closer to the nucleus is where you are most likely to find the electron. And again, it decays exponentially or some form of exponentially as you get away from the nucleus. And this is radius away from the nucleus. And what this looks like is your typical orbital, and meaning that for 1s, it will look like a sphere. And all you do is when there is 90% of the area under this curve, somewhere around here, that's where we define the orbital, because the orbital is the distance from the nucleus that says nucleus, distance from nucleus for the 1s orbital in particular, in which you draw the sphere that includes 90%, so includes 90% of the probability of finding the electron and that would be akin to drawing a circle or a sphere, somewhere around here. So there is probability outside of it, but it is exponentially decreasing. Okay. And if we were to do this, the probability density for 2s, so the probability density would come down, touch, come up, and go down. And this point right here where it touches is where it actually crosses the x-axis up here, and that is also going to be a node. And a node is a place where there is zero probability, in this case, zero probability density of finding the electron. And actually the node for 2s is actually pretty close to the maxima, or sort of inside the 1s orbital. Anyway, it's actually not a bad drawing. Okay, so the radial distribution function represents the total probability at a certain distance from the nucleus. It multiplies psi squared, which is the probability density, times the volume. And what we find from this is that the probability, yes, so this is where I should probably draw that probability. I'm sorry. So this is probability density. It is not the probability. So I should draw this same line here because this is actually probability. I apologize for that. So anyway, this has distance from the nucleus and total radial probability. And we would draw it probably, I would say, right about there. And so this is actually where the orbital comes from. So the total radial probability is going to be a sphere of approximately 130 picometers. And within that, there's a maximum probability of finding, and actually this shape looks pretty familiar to us if you remember the Boltzmann distributions for a gas. Goes up, comes back down, and there are similar mathematical functions. Anyway, there's a maximum probability of finding the electron at 52.9 picometers. Then the edge of the orbital, in which we have 90% probability, is approximately 135 picometers. And this is what we're going to be looking at in future slides. We're going to be looking at the functions for 1s, 2s, and 2p, and they're going to tell us about a lot of information about the energies of these, and we will talk about those shortly. Now, as I drew in a previous slide, and I said that 2s had a node. Nodes, for 2s, there's going to be a node, and that is a place with no probability of finding the 2s electrons, so the electrons in the 2s orbitals. And that's actually going to be where, more or less, you're going to find the 1s electrons. And so you can think of the nodes here as sort of optimized to keep the electrons apart. And then in the 3s, there'll be two nodes. And these nodes will be approximately where the 1s and the 2s electrons are. So you can think of the 3s electrons, so the sphere's getting bigger for n equals 3, but within that sphere there's structure that attempts to keep the electrons, negative things, as far apart as possible.